A viewer requested that I do a video about trying to measure a capacitor with a multimeter, and why you can't do that. I've done several videos on this topic, the two capacitor paradox where I discovered what was going on, and about using a buffer such as an op-amp to increase the input impedance of your multimeter so that you can, in fact, measure the voltage of a capacitor without draining it almost immediately, as well as a video on measuring the input impedance of your multimeter so you know what's going on. But here's a quick demonstration and a quick rundown of the math of why this happens and how. Let's set up a simple circuit. To make it as clear as possible, I'm going to use 32 volts, which is the maximum that my power supply can provide. I can confirm that's the reading I'm getting, right on the dot. And while I can charge a capacitor by shorting it directly with the power, and that'll be perfectly fine, for safety and for doing it the right way, I'll throw a resistor on there. And I'm going to use two capacitors, a 6.8 nanofarad and a 6.8 microfarad. They're different by 1,000 times. Let's start with the microfarad. So I'll just connect it straight through the power, and then I'll connect the multimeter over it. I'll just connect the multimeter directly over the capacitor itself and nothing else. So our final charge is going to be 31.7, 31.8 volts because of the voltage drop of the resistor. I could use a smaller resistor, but it's no big deal. The demonstration is there. So now what I'm going to do is just remove a wire from the resistor, which is going to leave the capacitor and the multimeter as the only circuit measuring voltage. And I'll let it go now. And you'll see it's dropping precipitously. You can watch it go down. It's not literally instantly. And the lower it gets, the slower it gets. And I can turn down the precision. You can see it drops down. So now we're getting down towards a volt. And then now we're below a volt. Once it gets down to 200 millivolts, you can see it going slower and slower. And watch any video or look at any tutorial for the charging and discharging curve of a capacitor. It goes faster and slower depending on the charge level. Now we're losing, single millivolts per second. And then, of course, if I turn it back up and reconnect the wire, it's going to charge very rapidly. It's already there in just 2 measurements. So as you can see, you can't simply use a multimeter to measure it. Now what happens, and first of all, when I take this capacitor out, I'm going to connect it to 2 traces that are together, short it to discharge it before I put it in the bag, so I don't accidentally use a charged capacitor later on. If this were a bigger capacitor or it were charged even more, I wouldn't want to just short it. You'd want to short it with a resistor or drain it with a resistor, but a little one like this, just short it, it's fine. So that was 6.8 microfarads. What about 6.8 nanofarads? I'm going to do exactly the same thing I just did. So I put the capacitor in, it's charged up, and then I'm going to do just like before and disconnect. And bam! Did you see that? Let's do that again. Let's charge it up. Charges up just as fast, and kerblam! It's gone. The exact same voltage, the exact same multimeter setting, everything was the same, just the size of the capacitor was different. And this one discharged immediately. Let's watch it on the lowest setting so we can catch the dregs. And discharge, and it immediately goes down, and it's less than 1 single millivolt almost immediately in just a few seconds. No need to short this capacitor, it has drained. Pretty clear now why it won't work. So let me show you what's going on mathematically. Hopefully you've guessed by now, but it's an RC network. When you have a capacitor and a resistor in series, regardless of other components, regardless of how you have everything else hooked up, just the capacitor and resistor, charging and discharging follows resistance times capacitance equals tau. And tau is time. It's in seconds. So farads times ohms equals seconds, which is pretty neat. But tau is the amount of time it's going to take for your capacitor from empty to charge or from full to discharge about 68-ish% of the way. It's the natural logarithm constant to some power, I forget. But we can also say 5 times, and that'll obviously be 5 times tau. But this is easier to work with in this case because it's, roughly speaking, completely charged or discharged. It's like 98, 99%, close enough. So the resistance times the capacitance times 5 is about how long in seconds it's going to take your capacitor to go from 0 volts to the volts you're providing, or from the volts you're providing, or it's providing rather, to 0 volts, charging or discharging, with just the capacitor and resistor. So it should be fairly obvious why, when I went from a 6.8 microfarad to a 6.8 nanofarad capacitor, the time went down. In fact, it went down by 1,000. This capacitance was divided by 1,000, which meant this whole thing is, so it took 1,000th of the time to completely discharge. So we went from like 10, 15 seconds to nothing. That's why changing the capacitor did that. And intuitively, capacitance refers to the actual amount of charge that can be stored on the plates, the actual maximum charge difference, regardless of the voltage. More capacitance, same voltage, is going to be more energy. So if we're draining at the same rate, because current, right, your current is literal number of electrons per second. So if you have more capacitance, that means more electrons. If you're draining at the same current, then you're taking the same number of electrons per second, but if you have more electrons, then it takes longer to drain. So the voltage goes down slower because it's not losing its charge as fast. But the important part is this R. What is this R? That's your multimeter. That is the input impedance. In my case, and go look at that video if you're not sure, but in my case, it is 1 mega ohm. 10 mega ohms is also common, and you can get more. But a 1 mega ohm resistor, so 5 times 1,000,000 times the capacitor size equals about how long that capacitor has before it's drained. It's that simple. This is why increasing the input impedance allows you to measure the capacitor. Because when I switch to an op amp as what's plugged into the capacitor, then the input impedance goes up to giga ohms, maybe tera ohms. It's drawing almost no current whatsoever. So the exact same thing is happening. It is still draining the capacitor the same way with an RC network. But when this starts getting many zeros added on, so does this. So the point is just to reduce the drain rate to below your measurement capacity. If you want to be accurate to within 1 millivolt, then you just have to have enough input impedance to be able to have it drain less than a millivolt in the time it takes you to measure. And just to round out the video, trying to read a capacitor without draining the capacitor, that's just the foundation of DRAM, the RAM that's in your computer right now. Every single bit of memory in that RAM is, essentially, with lots of bells and whistles, a capacitor. The capacitor's charged or discharged to have it be high or low. Then something high impedance is connected, such as a MOSFET, that reads that capacitor. The gate of a MOSFET mainly draws current when it is changing state, when it's going high or low. And when it's going high or low, it's being supplied by whatever's setting the capacitor, whatever's charging and discharging the capacitor anyway. When the capacitor's just sitting there not being charged or discharged, the MOSFET is not changing, and so it's drawing picoamps or less. It is drawing some, so you actually have to refresh DRAM every once in a while. You actually have to write the memory back to itself as that little trickle happens, but basically, you just read a capacitor with an incredibly high impedance measurement tool, such as a MOSFET, and that's memory. That's volatile memory. It's really small, and it's really cheap, and that's why you can have gigs of it on one little stick. So I hope that I have satisfied whoever requested the video. And for now, I'll be seeing you.